Our second speaker for this session is Maja Pantic, and this is very nice because complementing Barbara's research focus on human verbal behavior and its grounding in collaborative action is Maja Pantic's research focus on human nonverbal behavior and its applications to computer-human interfaces. The kind of human behavioral cues she's looking at are ones that you have to sense. They're facial expressions, body gestures, vocal gestures such as laughing. Maja got her PhD in computer science from Delft University of Technology and then went on to join its faculty. In 2006, she came to the UK to join the Department of Computing at Imperial College, where she's now Professor of Affective and Behavioral Computing. In 2002, she received the Innovational Research Award, I'm sure it sounds better in Dutch, from the Dutch Research Council for research on facial information for advanced interfaces, and then in 2007, a European Research Council starting grant for research on machine analysis of human natural behavior. Most recently, she received the annual BCS Roger Needham Award. So Maja's talk today is entitled Machine Analysis of Facial Behavior.
Thank you so much for this beautiful introduction. It is indeed my pleasure to talk after Barbara, because many of the questions that she raised in our research, at least we try partially to address. Mostly how you could analyze human behavior, right? So this talk is about machine analysis of facial behavior. And the first question that you could ask me is what this has to do with computer science. I mean, this has to do with psychology, human behavior, you know, human face. So you can, the human face is really fascinating. You can use it for thousands of things. So we actually use human face to identify other members of our species. We also use the face to judge the age of a person, or the gender of a person, or the beauty of a person. We even use the face to judge the personality of a person. This goes back actually to the Aristotle time, and whether this really is a correct assumption or not remains arguable. So in principle, if you think what we could use the face for, you immediately come to thousands of applications. So first of all, the security applications, because you immediately talk about identity, so it's access control and these kind of things. But also about other things, like, for example, medical purposes. And not that noble ones as Kirsten was talking about, but, you know, things like plastic surgery, right? So in principle, what is more important, more fascinating for me, is that the face is our preeminent means to actually recognize the emotions, the intentions, and the attitude of other people. So this goes back to this understanding of human behavior. Human face provides actually the means that we understand the human behavior, and then hopefully be able to use that further for our computer games, or human-computer interaction, or whatever else we want to do with computers. So this is why I got really interested in facial behavior analysis, machine analysis of facial behavior, and doing it in a fully automatic way. So this dates back to '96, when I was doing my Master of Science thesis in Delft. At that time, whenever I said to somebody, what are you doing? I'm doing the automatic recognition of facial expressions, they would look at me like I'm totally crazy. That's like absolutely impossible, right? So some of the first techniques that we built were, in principle, very simple. We used classical image processing and computer vision techniques, such as image histogramming and active contours tracking, to reason about basic emotions, prototypic expressions of basic emotions based on static images. So we would actually track these contours of the facial components like the eyebrows, the eyes, and the mouth, and then use a set of rules that would say, well, if in correspondence to the expressionless face, the contours change in a certain manner, we would reason that this is a certain emotion. So in this case, if the contours of the eyes and the mouth get smaller, you will actually reason that this is anger. So, however, what's the problem is that when you come to the real-world applications, such as this one, this is a camera mounted on a robot, and children, of course, playing with it because they can see what the robot is recording. You come to a question whether these prototypic expressions of emotions, 6 basic emotions, which are the happiness, the anger, surprise, fear, disgust, and sadness, are useful at all. We actually do not show these prototypic expressions in our everyday life. We show much more subtle expressions. That is the time that we decided not to go into the basic emotions recognition, but actually to concentrate on something else, which are the facial action units. So each of these facial actions are directly linked to facial muscle actions. So there is a very large muscle running across our forehead, and when you activate the middle portion of it, you will actually have the inner raised eyebrow raise. If you activate the outer portion of that muscle, you will have action unit 2, which is the outer, which is action unit 2. If you do this, that will be action unit 1 plus action unit 2. So there are in total 44 of those action units, and if you could recognize those 44 action units, you would be actually able to recognize each and every facial expression that we can possibly make. If you think that this is actually what you want to achieve in a video, to actually label each and every frame in terms of those action units. What is the point is that we have something like 10,000 different facial expressions that we can express, 7,000 of which we express on a daily basis. So if you think about 44 action units that could be used to represent all those 7,000 or 10,000 expressions, the dimensionality reduction is actually huge. So this is what we wanted to achieve. The reason is that why I wanted to go into the action units is that action units are completely agnostic. So you can use them to recognize basic expressions, like expression of sadness, right? This is a prototypic facial expression of sadness. Everybody shows it. Everybody can show it. That's not the point. The point is that we rarely show it in a daily life. The fact that my son is showing it is just that he learned that this is the way to get whatever he wants, right? Okay. You can also code in terms of these action units any non-basic emotional display or any expression of attitude or any given facial expression. Yeah? So what we wanted first is, okay, we had this system that we developed for the recognition of emotions, basic emotions, in frontal views. So we said, okay, we can use actually very similar techniques, image processing techniques, contour tracking techniques, track the contours of all the components that we are interested in, which are the eyebrows, the eyes, and the mouth, and then reason about different action units. The problem is that certain action units have very similar appearance, at least when you judge from static images from frontal views. So in case of this girl, if you look at the right-hand side picture, you cannot distinguish whether she is actually just has an open mouth or she has her jaw, which is protruding out. However, if you would use a profile view facial image, you will immediately cancel the possibility of action unit 26. So this is the time where we went into the so-called dual view facial image analysis, and applied similar techniques to the ones that we applied previously, only at this point we also had a contour of the profile, and then we reason about different action units rather than different basic emotions. So when I would say the eyes got more narrow, I would actually score action unit 7. And if I would say my lips or the lips went narrow, I would score action unit 24. And I will always check whether I have the same score in the frontal view and in the profile view. So actually I would have a kind of a merging of the rules, right? Well, this was quite amazing research in 1999 and 2000. The reason is that actually nobody else did this, right? However, I mean, it was the very first approach ever published in terms of automatic action unit detection. It was the very first one who dealt with the both views, frontal view and profile view, and so on and so forth. And many people adopted these approaches for their own purposes. However, the problem with this is that not all action units could be recognized. This is one of the problems, and the reason is that actually some of the action units cannot be represented in terms of movements of the points or changes in the contour of the facial components. A very good example is the dimple, which is labeled as action unit 14, which is a very typical action unit in contempt, in boredom, in irritation. So in all or very many real-world expressions, and you can detect it actually only from the change in the appearance from this dimple, right? You cannot actually say that the shape is different than, for example, the shape that you get if your mouth is just stretched. You don't see the difference, right? Another much more important problem with this approach is that we handle only static images. So let me first start with the second problem and show you this. So this is on the left, let me see, of the left-hand side you have an expressionless face, and on the right-hand side you have an expressive face. Can you guess what is this expression? Anybody? Okay, this is a very typical answer, and I completely agree. If you would look at this face, you would simply say, okay, his eyebrows are raised, his eyes appear to be more open, his lips are a little bit open. It is a typical surprise expression. However, if you look at the motion, you will immediately see that this has nothing to do with surprise. This is a typical way of greeting somebody, or in this case, this is my Greek student, of saying a Greek no, right? So it has nothing to do with surprise, okay? So this is when we started the research on analysis of facial videos and actually including the dynamics of facial behavior into our analysis. So the classical approach was to detect the face in an input image, detect a number of characteristic facial points, and then track these points in the whole video and reason about the motion of those points in terms of action units. So we did, and we still do, very intensively the research on facial point tracking. So we developed different tracking techniques for tracking facial points, and the one that you see here is a rather old one. It uses particle filtering framework, and it uses the assumption that all the points belonging to the same facial component, such as the eye, should have a specific constellation. So, for example, a point of the eye, which is the inner corner of the eye, cannot go, to your forehead or something. So you learn these constellations based on your training examples. As you can see, the tracker works pretty fine, and we could use it in many, many different occasions and applications. The problem was, of course, that when we went to very spontaneous data, like this data, where we asked people to watch different videos and we just recorded their reactions, you have the tracker which cannot deal with these constant motion that humans tend to make, right, with their head. So we then developed a different detector which uses incremental version of the robust kernel principal component analysis, the mouthful. You can imagine it as follows. We use a very specific image descriptors, which in this case are orientations of image gradients, and we learn in each frame how the change in the appearance happens. So in each frame, we adapt actually the model that we will track in the next frame. This is the reason why this tracker is much more stable. This is also the reason why this tracker can deal with some of the most difficult problems that we have currently in computer vision. And those are occlusions as well as very large changes in illumination, which are constant changes in illumination. So the video which you see on the right down or lower corner is actually a video of a guy moving under the foliage. This is a video made outside, and this is extremely important if you want to build robots or any systems that will work actually in outdoor environments, okay? So this is the first and absolutely first such method that can deal with this kind of situations. However, this tracker works pretty well also in a very low resolution videos, such as the video recorded in this robot scenario where we just recorded people doing things in front of robot. But again, it does not work at all well with the large changes in the head pose or with the very many nods and shakes of the head. So there are improvements that we need to do. When it comes to facial expression classification, a very classical method was this that I already explained, where we used the positions, or say the motions of the facial point to reason about the different action units. The first approach that we applied was a frame-based action unit classification approach, where actually what we did was we tried for each frame to reason about a certain action unit, okay? However, what you get then, because these points are not tracked very robustly, of course, is that you will have action units which are sometimes activated and immediately in the next frame deactivated. So you have this problem of on, off, on activation, which is of course impossible because facial muscles need time. The fastest activation of a facial muscle is 1/5 of a second. So if you talk about 30 frames per second, temporal resolution of your video, this is 6 seconds. This is the minimal time needed for a facial muscle to get activated. If you talk about 60 frames per second, we talk about 10 frames, right? So it's absolutely impossible that you have on, off, on, off. So this is just an artifact of a bad tracking algorithm, right? So how to deal with that? We said, okay, let's forget about per frame. What we're gonna do, we will try actually to feed the results of per frame classifiers into the hidden Markov models and then build the temporal dynamics model, which will say, okay, my action unit should be first in onset, then in apex, and then in offset, which means it will get activated, it will come to a peak, and it will get deactivated, right? So this is what you see here. You look at the action detector for the action unit 27, which is the jaw drop. The green line in the top graph is the onset class. The red line is the offset class. And Here, we feed that into the hidden Markov model, and you see how smooth the results you get, where the green are the true labels, and the red are the predicted labels in the lower graph. Okay. Except of dealing with this problem of temporal smoothing of the results, doing research on temporal dynamics and temporal evolution of action units has actually a lot of implications. Let me show you something. This is a video of two girls, obviously. One of them is entertained by a clown. The other was told to laugh. Okay? Which one of those is entertained by a clown? Who would say it is this girl? Okay. Who would say it's the other one? Okay. The majority said it's the other one. This is a typical answer when you go to computer science or the technical background meeting, okay? When you go to social background meeting, everybody says it's this girl. And they would be right, okay? Let me explain why is this the case. Okay, so look at the blue points. Those are just the corners of the mouth, okay? Here you see the trace of those points. What is happening with this girl is, okay, let me see, is this funny? Oh, yes, it's funny. Let me laugh a little bit more. This is a typical spontaneous laughter. It has multiple apexes. We think whether this is funny what we see, and then we laugh a little bit more. However, if you look at the other girl, what happened? They said to her, laugh. Okay, laugh. Laugh, 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 laugh. Now it's enough. Poof. Okay? So this is exactly where you see a very fast onset and a very fast offset. Okay? So this is extremely important if we can discover the dynamics of facial behavior. What we are actually able to do is to distinguish between acted laughter or acted smiles and a genuine one, or between anticipatory pain and the genuine pain, or, in fact, between deceit and veracity, okay? So it's very interesting. And that's why the rest of our research from, say, 2005 on is, say, focused on the analysis of the dynamics of facial behavior. So we developed different methods. One of those is based on, again, the tracking of the facial points in the frontal views and reasoning on the movements of those points, of course, in correspondence to the position of the points in an expressionless phase, which you usually capture in some of the first frames of the video, because when you start recording people, they don't laugh immediately like crazy. They just, or do whatever, they just watch the camera. So you get this neutral or expressionless phase. We also developed a different, a similar but yet a different method, which will do the event-based reasoning on the whole sequence, which will take the whole action unit into account and then reason about this onset, apex, and offset, and give that as the output for the whole sequence. We worked with also with completely different method, which is also motion-based, but it does not take the points as such into account. What it takes into account is the motion in the facial region. So what we do, we put a grid of points over the face, over the facial region, and we calculate the motion. You can do that using optical flow, for example, and then you reason what is the difference between the successive frames, okay? And you see the difference on a frame-by-frame basis in the top graph. What you see down is the sum of the frame-by-frame deformation, and then here we used just the first frame, and we applied this summed motion to the first frame. So to synthesize the video and see whether the synthesized video resembles the original video. And it does, but of course you have the artifact, there are no teeth because you don't see the teeth in the first frame, right? Okay, the methodology behind is ensemble learning classifier, doing classification based on the features such as the amplitude of the motion, the divergence and the curl, taking into in a frame-by-frame fashion, and then feeding that into the hidden Markov models that actually are Bayesian models that you can think as a temporal smoothers. Okay. The latest work that we concentrated on as well, among other things, was to actually try to predict the valence and arousal in continuous space. So rather than having the discrete emotions such as disgust, happiness, sadness, anger, fear, and surprise, we would actually try to recognize the affect dimensions such as valence and arousal. Arousal says something about how person is excited, and valence is how positive or negative a certain reaction is, okay? Of course, when we talk about human behavior understanding, having only arousal and valence is not enough. I mean, that's obvious. But you can always add another dimension. So you can add things like dominance, which is a very classical personality trait. You can also add other traits, like, for example, introvertness and extrovertness, which are all closely linked with things like valence and arousal. Or you can actually treat any other phenomena that you are interested in, such as stress or pain, as a dimension. So the whole idea is not to discretize the space, because we don't show the discrete expressions. It is, you have to go through a phase, right? So you have to show this laughter, or you have to show the frown, right? You don't just show it. It's impossible, right? There is a time development of this expression. So it is a continuous thing. And what we do, we just simply, actually in machine vision community, we just actually deal with this end product of facial behavior, which is obviously wrong. So we try to remedy that and deal with continuous analysis of emotions. So in order to estimate on a continuous time scale the valence and arousal in spontaneous facial behavior, we developed a completely novel method, which is output associative relevance vector regression, which takes into account the movements of the points, but not in the current frame, but in a number of frames surrounding the current frame, and then reasoning about giving the prediction about the valence and arousal. So whenever I talk about continuous, that means regression. It does not mean anymore classification in terms of machine learning. The results that we got are impressive. The reason is that we actually trained the whole system only on a single subject and tested it on a number of subjects. And the results are still really, really good. What you see here are actually the error rates. So having an error rate of 0.1 or 0.2 is really good. So I talked today about a number of techniques which we developed. Some of these problems, such as, for example, facial expression recognition in static face images, are considered solved. Some other problems, such as tracking, are not considered solved, and it is a question when they will be solved. So what you see, for example, down, this is our active appearance model that we developed, which, as you can see, deals extremely well with fast motion and with large changes in the head pose, but it cannot deal at all with changes in illumination. So what we need to do is combine the method that we have, a kernel method that we have up, and the method for active appearance models in order to get. So this is one of our current researches. We also worked on a number of other problems. We are actually the very first ones who deal with this problem. The method that I just described for valence and arousal prediction in continuous video is the only such method existing nowadays. Another method on which we work is the method that actually does not use the static faces for person identification. It uses the dynamics of the face to identify the people. And there are only a few works in psychology that say that this is possible. This is actually the first attempt to do this automatically, and we get really good results. So it is really interesting to go further into this research and see how the behavior distinguishes between people. Why I'm so interested in that is because, okay, I have a child. My child is very curious. He wants to actually open all possible and impossible applications on my computer. So some of the things maybe should be protected, right? So if I could have this kind of constant control, which is not based on a face, because he's extremely smart. He would take my picture and put it in front of the camera, right? So the point is that you have to trick them somehow. So this would be one way of doing that. Another line of research which we started is using 3D videos. Actually, those are the videos recorded by 3D camera. So you have actually a depth information, but over time. Okay? So why is this of importance is because certain areas, such as these areas around the jaw, are extremely important for example, detection of stress. But we cannot reason at all what is going on there because we don't see, definitely not from the point. Also not actually for anything what is frontal view and appearance-based model. So this is why this is actually interesting. The method itself is exactly the same as the one I already described to you, which uses the grid of the overlaid points. We only now have the grid of the points in the 3D, and we have a number of projections that we use for the analysis of, in this case, expressions. 6 basic. Another interesting part, which I actually believe is pushing the borders further and answering a lot of questions in not only computer science, it actually answers some of the questions in behavioral sciences and psychology as well, is the studies of interpersonal interactions. What was the problem with these studies is that people did not have time and, I don't know, nerve and I don't know, persistence to sit and find a way to synchronize all the sensors that you use for recordings, synchronize it to very high precision, which is absolutely necessary if you want to study things such as mimicry. Mimicry is extremely important. The way we mimic each other says something about the rapport. It says something also about for example, whether we like somebody, whether we dislike somebody. It says something about flirting, says something about who is the boss and who is the employee, right? Because bosses tend not to mimic, and employees tend to mimic in order to be liked. So these things happen unconsciously, okay? But they are extremely important because if we can analyze these kind of things, we could actually understand much more of what is going on, what is the human behavior. Things what I said unconsciously, this is extremely important as well. Think about when you go into the bus, you sit by somebody, but there are 2 empty places. You will sit on one of them. You make a lot of processing in your brain where you will sit. This depends on who is the person next to one side, who is the person on the other side, whether this is close by the door, thousands of decisions. This happens unconsciously 30 milliseconds, okay? If we would be able to analyze these kind of things automatically, we would actually be able maybe to open some of those doors, how our brain functions, how we function, okay? So what are the lessons learned? The first one is that we should not work with acted expressions. This unfortunately, still, 85% of computer vision community work works with acted expressions. However, acted expressions are person independent, they're extremely exaggerated, and they're short-lived. However, if you deal with spontaneous expressions, you have very subtle changes in the behavior, plus these are person dependent, okay? So if you train your methods on acted behavior, they will not work on spontaneous behavior, okay? First of all, due to subtlety. Second, because of the person dependence. The second thing is the dynamics of the behavior are extremely important. As I said, my group is still one of the very few groups who deal with this problem. There are problems with this. I mean, one of the things is having a good data set for that. So we developed the data set. It's publicly available currently. However, there is also a lot of machine learning behind. So, of course, maybe that's a problem. However, I believe this is the cue. So this is what we should do. The third and very important lesson is that actually we should not discretize the space which is originally continuous. Behavior is a continuous phenomenon. Discretization in any way is not a good thing. So it's much better if you work with continuous, dimensional, multidimensional interpretations. And the last thing is exactly as many people also remarked so far, there are no excellent work without excellent people. So I'm really grateful to my group because the work which I presented is due to them. Thank you for your attention.
Okay. Are there questions for Maja? Oh, John.
Thank you. Great presentation. I had two questions. The first one was about spontaneity, which is the point right at the top. Absolutely, the direction you're going seems to be incredibly promising. I wondered about lying, because even in spontaneous behavior, if you have lies, where do they come from? So if somebody's instructed to lie and then behave spontaneously, it's not a real lie. So you want spontaneous lies in the spontaneous behavior. So that was question number one. It was just a question about how you get that fantastic data that you're getting in the spontaneous data sets. And the second question was, you alluded to going to 3D, and I wondered whether you'd also looked at going into infrared if you're adding dimensions to the data set. Thanks.
So regarding the lies, the way we do is we actually give the choice to people either to lie or not to lie. It's up to them. If they lie and they pursue the interviewer that they are telling the truth, they are getting the reward. If they are caught, they don't get the reward. Okay? So it's very important that you work with incentive. This is a very sensitive topic. So it is, if you do not have a good incentive, you will not get the good data. However, the data that we are releasing is not about the lies. It is the data about, in fact, we wanted to have conflict data. We never managed to have conflict data because what we did stupidly, that was really my mistake, is that, in fact, we brought people who did not know each other. So, of course, they wanted to like each other. So it's the data at the end, we call it a mimicry database, because they only mimic each other instead of having a conflict, okay? So but it's a fully spontaneous data. We just told them one should persuade the other to give him the room, because they were like flatmates trying to, get a new flatmate, right? That was about that. Infrared, well, I worked a little bit about the thermal domain. It is a very interesting domain. It is different than infrared, but it can give you interesting data and information. However, the problem is that the current commercially available cameras for thermal acquisition are, first, very expensive, second, they're really bad. So what you need, what happened is that I was very lucky that I have some people in the States who, again, have very good connections with the Army. So we got to use a thermal camera of some $300,000 in order to record some of the thermal data. And you can definitely see, for example, when people lie, that they flash. So this you can see, but you really need this kind of camera, and this kind of cameras cannot be bought, you know, commercially. So that's a little bit of a problem. I hope I answered.
I think the third part was 3D was the third part?
That was just another dimension.
Okay.
This is also about the naturalistic behavior. So I completely understand from your examples why you wanted naturalistic behavior. But I'm wondering what you do about the logical problem that if you're trying to get naturalistic behavior to be a training set for facial recognition, if it's naturalistic, so you haven't told somebody, be happy, be sad, how do you know without falling into a sort of logical loop that you're correctly identifying the expressions you're seeing in order to use them in the training set?
So how it goes is when you're working with simple things, such as happiness, you simply give people to watch funny videos. This is, and they laugh. So this is a simple way. However, if you want more complex data, like the data I showed, this is the main data, you have, of course, the problem. So at that point, what we do, we give to psychologists to annotate valence and arousal, because they are trained to annotate valence and arousal. However, again, we have a problem, because each and every person has his or her own opinion of what is valence and what is arousal and how they should score it, okay? So although they are trained, they still have a lot of divergence in between them. So you have to ask many of them to do that. There is a third problem, and that is the delay between the brain and how you annotate, okay? So for some people, take it a shorter period of time to annotate valence and arousal or whatever dimension you want them to annotate than for the other people. So you have to take that into account. So actually what we do, we first have for each sequence a so-called calibration moment where we first measure what is the delay that people will have between the process and give the answer of valence and arousal, and then we actually apply that for the whole sequence. The first problem of having the divergence between people we solved in a very fancy manner, and that is we developed a novel probabilistic dynamic version of component correlation analysis, which actually when you apply, you get the alignment of the time series, because you can see actually the annotation as a time series. So we have the alignment of time series, time wrapping of the time series, and so we get the ground truth from 15, 16, 20 annotators. So it's quite good.
Thank you.
Okay, one final question, Graham.
At the moment, some psychologists in their laboratories, when they're trying to give stimuli to human subjects and see how they react, they have to spend ages hand-coding videos for the facial expressions in the reactions to see what the reactions have been. Is this technology something that could be used in a psychology lab robustly to replace that?
This is the whole point. So we actually developed a number of tools which are all available from my website. So if you are interested in this, just go, you can Google iBug or my name and you will come to the website and you can download. We release all of our tools. So search for action unit annotation. Of course, you will need to track the points. We give also the trackers. So the ones for action units, you have appearance-based, which work on LBPs, and for relatively frontal views, LBPs are local binary patterns. This is appearance-based features. All appearance-based features suffer from changes in the head position. So if you have nearly frontal views, it will give you pretty good results in terms of action units, okay? So we do release the code. So the technology is currently available for that. And we collaborate with both Jeffrey Cohn, who is one of the known psychologists in University of Pittsburgh and Carnegie Mellon University, as well as with Judy Bourgon, who is working in University of Arizona on lie detection, as well as with Roddy Covey and others in UK.
Okay, rather than ask for other questions, I think we'll thank both speakers and go enjoy some tea.
This production is brought to you by the University of Edinburgh.